SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process by great poet and Nobel laureate Rabindranath Tagore. He says, "Do not limit a child to your own learning, for she was born in another time." This is a very great statement which is applicable to all of us. And we parents generally thrust upon our ideas and aspiration on our children, which is really a crime according to me. So, therefore, I would request all of you viewers who are attending this lecture, please do not do that mistake whenever you will be taking care of your own children. So, let us recall what we learned in the last lecture. In the last few lectures, we have discussed about details on solid propellant rocket engines, and we have covered various aspects, and today we will be discussing about the liquid propellant rocket engine. If you compare the liquid propellant rocket engine to the solid propellant rocket engine, it is quite complex in nature. However, its combustion chamber is quite compact, as it does not carry any propellant, unlike in solid propellant where the propellant grain is placed inside the combustion chamber. And it is being used nowadays very much because of its high performance, as we can achieve specific impulse of even around 450 or 30 by using cryogenic engines like liquid hydrogen, liquid oxygens. And it is also quite easier to throttle, and so that you can change the thrust level and even sometimes direction also you can change by using the thrust vectoring control system. However, with advancement of the technologies, now one can get a liquid propellant rocket engine with higher thrust, and even it has been used as a booster rocket, as a part of booster rocket, that is in your GSLV we do use it. So, therefore, it is a very important and quite complex in nature. We will be looking at some of the things, and let us consider the example of V2 liquid propellant rocket engine, which was designed and developed by the Germans and was used as a missile in Second World War. And keep in mind that this liquid propellant rocket engine was conceived by Robert Goddard in around 1915. However, he worked hard and demonstrated in 26 March 1926, and it was not that very successful. However, it was demonstrated that it is possible to have a liquid propellant rocket engine, and that can produce thrust. So, let us look at the schematic of a V2 liquid propellant rocket engine, which is shown here, and this we had discussed earlier, but just to recapitulate, if you look at it, is having worded and automatic gyro control system, and this portion is basically payload which a missile has to carry, and it is having the propellant chambers like which will containing alcohol water mixtures and liquid oxygen tank here, So, which takes a major portion of this missile, and your combustion chamber, which is a very small one. If you look at this is your combustion chamber, and the nozzle which is very small, and the nozzle, this is your CD nozzle, like conversion diversion nozzle. This is your conversion diversion nozzle, which is little bigger. And keep in mind that it is having also an systems of ignition in which hydrogen peroxide is being used, and wants to feed this the propellants, liquid propellant. For that, this having turbo pump system or the feed system. And beside this, there is a cooling system. If you look at this is your alcohol inlets for cooling the rocket nozzle and also combustion chamber. And beside this, it is having also compressed nitrogen pressurized bottle, which are used to pressurize the propellant to start with, and after that, of course, the turbo pump system will be taking over for pressurizing propellant such that atomization can take place properly. And it is having also a air vane, jetta vane, and as a part of the wing, such that you can control this rocket engine. So, it is a very simple and primitive liquid propellant rocket engine, but however, it is looks to be quite complex in nature as you could perceive from this. And liquid propellant engines can be divided in two categories. One is monopropellant rocket engine, other is bipropellant rocket engine. In case of monopropellant rocket engine, a single propellant is used to produce the high pressure and temperature gas, which can be expanded in nozzle for producing thrust. In case of bipropellant engines, the liquid fuel and liquid oxidizer are used to burn in a combustion chamber, separately being fed through two different systems, like as it is shown in the V2 liquid propellant rocket engines. Most widely used, particularly in current time, whenever we need to have the high specific impulse, is the liquid hydrogen and liquid oxygen cryogenic engine. And beside this, the propellant systems is also used in case of hybrid rocket engines. Of course, the hybrid rocket engine means a combination of both solid and liquid propellants, which is being used, and the design will be similar, particularly for the liquid propellant stream, to that whatever it will be done for the liquid propellant rocket engines. So, we will be now discussing little bit more about the various systems in case of a liquid propellant rocket engines, what we can have. Let us look at a basic configuration. And when we looking at a basic configuration, that already we have seen, now we will be looking at in a schematic diagram. Let us identify what are the major systems of a typical liquid propellant rocket engine. So, for this purpose, let us look at a schematic diagram, and if you look at this diagram, we will be having liquid oxygen and liquid fuel, which is a tank. These are basically tank, and from this tank it is fed to the system with the help of liquid oxygen pump, and this is a centrifugal type of pump, and so also the liquid fuel, and this is being run by a gas turbine, and which will be producing power, and through the gearbox the speed is reduced and then it connected with the shaft. This is your shaft. And keep in mind that to run this gas turbine, we need to have a gas and which is being produced by using the liquid fuel and oxidizer. This is basically known as gas generator or combustors. And then this liquid oxidizer and liquid fuel are injected. This is your injector head, in which there will be atomizers which will be there, and that will be converted into spray. And in order to have ignition, so you should have a igniter, and this is your combustion chamber. Where the fuel and oxidizer will be atomized, mixed, and also burning to produce high temperature, high pressure gas, high temperature and pressure gas, which will be expanded in a nozzle to produce the thrust, and this is your nozzle. And keep in mind that there will be a cooling system. Generally, the fuel is used as a coolant for cooling the not only the rocket nozzle or the CD nozzle, but also the combustion chamber. So, if you want to summarize what are the major system of liquid propellant engine, then you can say it is having the propellant feed system, it is having the injector systems or injection system, propellant injection system, or then it will be having combustion chamber, which I have already shown, and ignition systems. And ignition system is not only the igniter, is having lot of other things also included, and nozzle, and of course, the cooling system. So, these are the things which are looks to be very simple in schematic diagram. We will see it is not that simple, it is quite complex in nature. Let us look at the types of liquid propellant rocket engine we can have. We have already discussed them at length, but we will be just recalling some of these concepts, this classification what we learned earlier. If you look at, depending on the type of propellant, it can be divided into the two categories. One is hypergolic propellant rocket engine, other is non-hypergolic propellant rocket engine. In hypergolic, as the name indicates, the propellant does not need any ignition energy to be initiate the combustion, whereas the non-hypergolic propellant, in case of a hypergolic propellant engines, it does not need any ignition energy to initiate the combustion, whereas in case of the non-hypergolic propellant rocket engine, one has to provide the initial ignition energy such that the combustion can be initiated. And beside this, the depending on the whether a single propellant or a double propellant, we can divide into monopropellant rocket engines and also the bipropellant rocket engines, and of course, one can go for a higher kind of thing, but generally people use monopropellant rocket engines and bipropellant. In case of monopropellant, a single propellant is used such that it can be decomposed into its constituents whenever it will be coming in contact with catalyst or some ignition energy, such that high temperature and pressure gas can be produced easily. But in case of bipropellant rocket engine, generally both the fuel and oxidizer liquid propellants are really separately being injected into the combustion chamber. It can be hypergolic, it can be non-hypergolic. So, that also can be there, and similarly monopropellant can be hypergolic propellant, can be non-hypergolic propellant, depending on that. So, let us look at a typical engine of a monopropellant rocket engines, and it is quite simple in nature. And as it can be seen here, there is a high pressure gas which will be stored, and that is used to really feed from the propellant tank into the combustion chamber of the rocket engines, which is shown here. So, this is your propellant tank, and this propellant tank will be basically pressurized by high pressure gas which is stored in a vessel. The high pressure liquid propellant will be getting into this combustion chamber. It is passing through the catalyst bed. There are various kinds of monopropellant which are being used. We know that some of them are the hydrogen and hydrogen peroxide and hydroxyl ammonium nitrate and others. But let us consider a simple case of a hydrogen, and for hydrogen generally the catalyst is being used is the iridium, and there will be some aluminum granules which will be there, and basically activated iridium is adsorbed in a small granules of porous alumina and having diameter of 1.5 to 3 mm, and which are packed here. These are alumina granules and coated with activated iridium. So, this forms the catalytic bed, and keep in mind that how much of gas it can pass through this bed will dictate the how much of propellant can be burned, and the surface area of that is very important, and also how much contact one can have, and these can be judged by the permeability of catalytic bed is dictated by bed loading factors, and that is expressed in how much of grams of propellant it can allow through the this surface area per unit time. And keep in mind that the extent of the decomposition of the monopropellant will be dependent on this contact surface area and extent of also the permeability, and depends on also the size of this porous alumina, and also how much the quantity of activated iridium it can come in contact with the monopropellants. So, let us look at the hydrogen which gets decomposed when in come in contact with the iridium catalyst, and it can undergo a reaction that is 3 moles of hydrogen is decomposed into 4 moles of ammonia and 1 mole of nitrogen, and this ammonia is further decomposed into hydrogen and nitrogen, and keep in mind that this reaction is exothermic in nature. This is exothermic reaction, and this is releasing 336.28 kilojoules of energy, and but the second reaction, the 4 moles of ammonia is decomposed 6 moles of hydrogen and 2 moles of nitrogen. It is an endothermic reaction, it is giving 184.84 kilojoule. And of course, you can get a adiabatic temperature of 1700, and when it is operated at 7 megapascal, it gives something specific impulse of 245 seconds. And as I told earlier, the extent of hydrogen decomposition depends on the extent of its contact with the catalyst, its size, and also the configuration of the bed. So, therefore, one has to design it properly to maximize the decomposition of the hydrogen or any other monopropellant, such that one can get a higher specific impulse and also the higher efficiency. So, let us look at bipropellant rocket engines. In the bipropellant rocket engines, I have shown a very simplistic schematic diagram, where this is your fuel tank and this is your oxidizer tank, and it is similar to that monopropellant. Only thing is that the two lines are there. One is your fuel is passing through this, this is your pump, and through this control valve it moves over here. Keep in mind that it is going to the nozzle and it is act as a coolant, and not only for the CD nozzle, this is your CD nozzle, but also the thrust chamber or the combustion chamber. And what it goes, then it is basically converted into spray. So, also the oxidizer which is passing through here, it will be injected into that, and there will be injector head which is not being shown over here, and this is your injector head. And depending on the kind of configuration of atomizers, whatever is there, it can have different spray patterns and they can mix and everything. So, this is only difference what you could see here, that it is having a gas generator which will be running this turbine, which is not shown properly, but this is your turbine, and turbine will be running this both the pump, both the fuel and oxidizer pump, and there will be also gearbox in this which is not shown. So, if you look at it, comprises all the systems except maybe ignition system. There might be a igniter over here, right, which is and if it is a hypergolic propellant, maybe ignition system is not required. So, let us look at the basically cut away model of a actual liquid propellant rocket engine. It looks to be quite complex in nature. So, if you start with from the top, it is having a gimbal which is mounting. This is gimbal mounting, and which is used for thrust vectoring, and this is your liquid oxygen elbow which is passing through that, and it will be passing through these flow straighteners, and there is a liquid dome which will be having here. And keep in mind that this side is the fuel valve mounting, and then elbow is here, and it will be passing through that. This is your fuel valve flange also similar to the liquid oxygen, and it is passing through the LOX feed and then fuel feed line, and this is your injector plate which is here. This is your injector plate, this is similar to that injector plate, and which is having several tiny holes and being placed in a proper way, so that it can not come in contact with each other, however it will can convert into spray. And beside this, this is your pyrotechnic igniter, this, and this is your electrical lead, and there is also sealing ring, because you will have to seal the both the liquid fuel and the oxidizer, and there will be lot of sealant which will be used. And this is your thrust chamber, and of course, this is your fuel feed line, and this fuel is being coming through this valve, and which is cooling this thing. So, that fuel tubular, this is your fuel which will be passing through that, the tubular fuel cool tubular valve, and as I told earlier, fuel will be used as a coolant for cooling the both the conversion diversion nozzle. This is your diversion portion, and this is your conversion portion. This portion is your conversion nozzle, right, and this is your throat area, and then to stiffen the to strengthen that, stiffening band is being used, because this is the weakest portion of the entire rocket engine, where the heat flux will be passing through that will be maximum. And beside this, there are several other components which are there. If you look at, it is containing almost all the systems, and what we can recall, the systems are injection system, and of course, the propellant feed system is not being shown here. it is above it. It is only the thrust chamber and rocket nozzle. It is having ignition system, nozzle and then cooling system. So, if you look at this is quite complex, and when you design each component and when you look at each component and its efficacy and also the assembling them properly and testing, it is a Herculean task. And I think the engineering point of view, it is quite complex in nature. We may not cover in this course all the design aspects and also the fabrication aspect. We will be only looking at general basic principle of that. So, with this I will stop over, and thank you very much, and in the next lecture we will be discussing more about the how we can atomize the liquid propellant such that the complete combustion can take place, so that we can improve the combustion. Thank you very much.